Hi, my name is Daria Tansel, and I work with Jacob Brenneman with our advisors Gary Feder and Rahul Panat at Carnegie Mellon University. And today I'll be presenting our work on the fabrication of stretchable electronic interconnects by aerosol jet printing. Thin stretchable substrates with embedded electronic circuits enable comfortable skin-wearable health monitoring applications. PDMS, or polydimethylsiloxane, exhibits appropriate properties for the development of stretchable sensors for health monitoring applications. However, fabricating stretchable electronics by conventional processes at high temperatures needed for solder reflow can affect the integrity of the stretchable materials. In this work, additively manufactured, stretchable, low-resistance, insulated interconnect embedded in 30 to 60 micron thick PDMS substrates survive an applied strain of up to 40%, which is suitable to be used as skin-wearable electronic decals. The key feature in the process are the sintering at 300 degrees Celsius of aerosol jetted silver wiring and its encasement with aerosol jetted polyamide layers to form a tough insulating jacket. The direct digital printing on and within PDMS provides rapid design flexibility and a clear path toward interface stress management for integration with embedded functional chips. The aerosol jet printer has pneumatic and ultrasonic atomizers that convert the ink into aerosol droplets, which is focused at the print nozzle and is capable of printing features down to 10 microns. In this study, we conducted a design of experiments which consists of 3 canonical wiring patterns of varying angles of curvature of 90, 180, and 270 degree serpentine meander designs of silver encased in polyamide wiring. The samples were characterized in pool tests using an instron while simultaneously monitoring 2-point electrical resistance. In addition to the angle of curvature, the number of overlapping layers or thickness of jetted polyamide and silver were also compared in this study. The fabrication flow is described in these images here. First, shown in A, polyacrylic acid release layer, or PAA, is spun cast on a silicon wafer. Next, in B, PDMS is mixed with 20:1 base to curing ratio and is spun cast on top of the release layer. In C, polyamide-based insulation is deposited by aerosol jet printing. Then in D, solvent-based silver nanoparticle ink is then jetted. In E, a second encapsulating overlayer of polyamide is jetted using the same parameters as the first polyamide layer. And for the final step in F, samples are cut and released in saline to dissolve the release layer overnight. The overall sample thickness is less than 50 microns. The silver nanoparticle wiring was sintered at 300 degrees Celsius in vacuum chamber at 1 torr for 4 hours, and thermal treatments at 300 degrees Celsius at 1 torr after each step is done to mitigate issues with multi-layer curing. For biomonitoring applications, we can print 200 micron tall pillars to interface with the skin or other external equipment. Once fabricated, the samples were then tensile tested in an instron machine and stretched at 2 millimeters per minute. These videos show the real-time load versus extension and 2-point resistance with time plots as the sample is being stretched. From the load versus extension plots, you can see a sawtooth pattern, which is possibly due to the cleavage failure occurring between the polyamide and PDMS at different points across the serpentine. The parameter we are mostly interested in is the strain of failure, which varies depending on the angle of curvature. The 270-degree angle of curvature had no initial connectivity prior to being tested, so the resistance plot is excluded here. The varied thickness of polyamide and silver layouts was also investigated, but did not have a significant effect on the strain of failure characteristics of the interconnect. However, thicker layers of polyamide resulted in higher instances of delamination during the final curing stage of the top layer of polyamide. This undesirable behavior is a result of vapor-driven delamination, where the absorbed moisture in the previously cured polyamide is able to vaporize at the heterogeneous silver interface and provide energy for delamination. We have published work on this understanding, and it is cited here as well. For the results, the 180-degree meander angle resulted in the best survival to 44% applied strain with 2-wire resistance of 100 ohms. The 270-degree meander falls with an average failure strain of 41%, and the 90-degree meander resulted in the lowest average strain to failure of 15%. In conclusion, aerosol jet printed stretchable interconnects are demonstrated with multi-material construction with a maximum failure strain of 44% for the 180 meander angle design, and images during the stretch and the corresponding mechanical and electrical data are presented here on this slide. High temperature processing of up to 300 degrees Celsius is demonstrated in an additive manufacturing process flow compatible with solder reflow temperatures. We would like to thank the National Science Foundation and Highmark Health for supporting our project. Thank you for your time, and if you have any questions, I will have a Q&A on March 24th from 10 to 11:15 a.m. through Zoom. Additionally, you can also email us at the listed emails. Thank you.